Okay. So today we're getting into running a kind of methods. One of the most popular time-stepping methods for ODEs, because they're not that hard to implement, and they're also quite accurate. So they have a lot going for them. And for people like me who are trying to design other methods for solving such equations, it's a lot to compete against. Okay, but what we're going to see today is that designing Runge-Kutta methods can be a real pain. So I'm going to step you through design of a simple one. So where I left off last time, and this is what you should have in your notes, is a multivariable Taylor expansion for f of ty, and we're going to make use of that here. Okay. So to give you an example of how design of a such a Runge-Kutta method works is first what you do is you choose a form of your method. So I'll illustrate that with this example. Okay. In this case, yn plus 1 is equal to yn. So it starts out like Euler's method that you've just seen, but it's a little more elaborate than that. So h, and I'm going to highlight unknown parameters. So you have this unknown parameter a1, and then f of tn plus alpha 1, so that's also an unknown parameter. And then f is a function of t and y. So our y value will be y sub n plus beta 1. And this is our third and final unknown parameter. Okay.
A sub 1 again.
Oh, yeah, so A1 and alpha 1 are just constants that we need to figure out. And beta 1 will be a function. Well, beta 1, yn could be a scalar or a vector. Because this is good for ODEs or systems of ODEs. So beta 1 is the same kind of animal as yn. In other words, something that can be added to it. So when I say choose form of method, in this case, we're still only going to evaluate f once, like Euler's method, but we're going to evaluate it at a different point and possibly scale it by something in the hopes of getting higher order accuracy. Now later we'll see other Runge-Kutta methods that include more than one evaluation of f in order to get higher order accuracy still. Okay. So then what we do is we match Taylor expansions of of y and f. So any evaluations of f, you're going to Taylor expand those. So that's a multivariable Taylor expansion we're talking about. And you're going to match that against a Taylor expansion of y. And any Taylor expansions should be done around t sub n, since we're trying to get from tn to tn plus 1. And we do this in such a way as to maximize the order of accuracy. And we're only going to look at the local truncation error. We're not going to do any global error analysis because basically what we saw last time, there's no need to do global error analysis for one-step method. If you can show that it's consistent up to a certain order, the local truncation error, the global error will have the same order. So we no longer have to go there. And Now, the more evaluations of f you have, the more flexibility you can have, because you have more parameters, and you can increase the order of accuracy. But we're going to see how much we can get from just having one evaluation of the f. So it is, we're going to match Taylor expansions, and you'll see what I mean in a moment. The more terms we can match up with these degrees of freedom that we have, the more terms we can match up, the higher our order of accuracy can be. Okay, so this is our design process. Pretty simple to describe and a pain to carry out. Okay, so
So we're scaling it with A1.
yes.
So that's the scaling factor.
Right. Okay.
Will they have to be like lower than 1?
Well, we don't know. Yeah, that's the mystery that we're going to solve. Whatever gets us the order of accuracy, whether it turns out to be equal, greater than, less than 1, we don't care. We just want order of accuracy. And the thing is, since we already know that we can get first order accuracy just by choosing this to be 1, this to be 0, and that to be 0. That's Euler's method again. Can we choose something different that will get us second order accuracy, for instance? That's what we're here to find out. Okay. So off to our board we go. All right. So like I said, we're going to be matching up Taylor expansions. Okay. So the first thing we match up is Taylor expansion. So this is a single variable Taylor expansion. That's more familiar to you. Of y of tn plus 1 around t sub n. Okay. So y of tn plus 1, and we've seen this Taylor expansion before. We used it to come up with Euler's method. So that would be y prime of tn times h, because this is tn plus 1 minus tn. And then we have 1/2 h squared, y double prime of tn, and I'll go out to one more term, 1/6 h cubed y triple prime at some unknown point, I'll call squiggly n. Now, how far do you go? You want to make sure you go out far enough so that you have enough terms to match against your other expansion and cancel as much as you can. If you find that you've run out of terms and you haven't determined all your unknowns, like A1, alpha 1, beta 1, then add on more terms until everything is settled. So you can always go up further if you need to. But this will be enough for our purposes. Now, we're trying to figure out what to do with an evaluation of f. So what I'll do is I'm going to replace these derivatives with derivatives of f. So I have, I'm also going to show you some, I'm going to change I'm going to try to simplify notation just because there's going to be a lot of crap I'm going to write. So, so for instance, I'm going to drop certain subscripts and so forth just to simplify things. So y prime is equal to f. And we plug into f ty. We still have the h. And then y double prime is going to be the derivative with respect to t of f at ty. And then h cubed. Y triple prime will be the second derivative of f at It's unknown time, which I'll call it C, and y like C. Okay, so just to simplify things, instead of writing Tn all the time, I'm just writing T. Instead of writing y of Tn all the time, I'm just writing y. And that's just to simplify what I'm writing for the sake of matching up Taylor expansions. In other words, I'm giving myself license to be a little bit lazy. Okay. Now, before we go any further, if we take this and match it up against what I wrote earlier for a general form of our method, the first term is just going to be yn. So this part is already matched. We don't need to do anything with that. And we have h times other stuff. So it's really, really we want to match all of this except for a factor of h that's already matched. So we want to match f of ty plus 1/2 h, derivative of f, plus 1/6 h squared, second derivative of f. Okay. All right. So we want to match this against what else we have in the numerical method. So this is the second thing we need to expand. And that's going to be a1 f of t plus alpha 1, y plus beta 1. So here, I'm using the same lazy notation. Instead of writing tn, I'm just writing t. Instead of yn, I'm just writing y. So at least I'm being consistent. So I want this to match up against this. But the thing is, right now, I have no way of matching these up the way this is written. Because here I have f of ty, here I have f of upper values. So now is where I'm going to use the multivariable Taylor expansion from before. I'm going to take this and expand around ty. So what does that give me? So using the multivariable Taylor expansion I did at the end of Monday's class, I'll have, well, a1's multiplying everything. And I'm going to have f of ty. So that's my first term in my multivariable Taylor expansion. Plus partial of f with respect to t of f times a change in t, which is just h, plus partial with respect to y times a change in times the change in y, which is just going to be, well, what is my change in y? It's beta 1. Okay, so those are my first derivative terms.
Hey, Dr. Lammers.
Yeah.
Why did we lose an H on the second line, the one that's in the big box?
This?
Yeah.
Oh, because if we compare this to
Divided by h, right?
that, I have an h sitting there,
Okay.
so I know, and
That makes sense.
okay, all right, yeah, and I have an h everywhere in here, so I just drop an h. Okay. Okay, so now I have my first derivative terms lined up. Now, as for my second derivative terms, I'm going to have a few of those. So I'm going to have 1/2 partial, second partial with respect to t of f times a change in t squared, so that's alpha 1 squared, plus second partial with respect to t and y, the mixed one, change in t, change in y, plus 1/2 second partial with respect to y change in y squared, and so on. I'm not going to write the other terms. In fact, I'm not going to need the other terms because the terms I've written down will be enough to figure out what all the parameters should be. Yes?
Why don't we use h for the change in t there, but then alpha there?
Yeah. That's supposed to be alpha 1 here. Okay. Well, that's right, because that was a change in t up here, but not down here. And I was like, why did I think that? Okay. All right. So now we have a somewhat clear idea of what we're supposed to match, except now, okay, so I'll box this kind of as best I can. Okay, so again, this is what we're supposed to match up, but now it's the top part that's not quite the right form, because down here I have all these partial derivatives of f with respect to t and y. Here I only have like total derivatives of f of ty with respect to t, where this would involve derivatives of f with respect to both t and y, because y is understood to depend on t. I need to work these out, and I will in a moment. But before we go any further, can anyone tell me, if you see what's boxed here, what we're supposed to be matching up, we have three unknown parameters, a1, alpha 1, beta 1. So can anyone tell me if anything we can match already?
F of ty.
All right. So if we just focus on the first terms, what does that tell us?
A1 is 1.
What?
A1 is 1.
Yeah, a1 needs to equal 1. That's just to have these first terms match. So at least we've nailed down one thing.
All right.
But it's going to take a little more work to figure out the rest. Okay.
Well, the ddt of f of ty, how many ddt's are there? There's only one ddt, right?
Well, the thing is, here we're going to have first partial derivatives after we work this out, which we will match against these terms.
These two terms. Yeah.
But only once we work that out are we going to see what we're really going to get there.
Right.
Okay, so that's what we're going to do next. Okay. So now we can ignore, okay, so these terms match up, we can ignore those now. So let's see what's supposed to match up next. So the total derivative with respect to t of f of ty, where y depends on t, times 1/2 h. Yes, and we're going to focus on the first derivative terms. Partial of f with respect to t times a change in t plus partial with respect to y, change in y. Okay, so now we need to work out this. So this is going to be, I will have h over 2, and this is going to be partial of f with respect to t plus partial of f with respect to y times dy dt by the chain rule. But what is dy dt?
Y prime.
Which is
Yeah.
f. Yeah. Okay, so I can fill that in. All right, so plus partial of f with respect to y, ty f of ty. Okay, so now we're matching all this against all this. forcing these to be equal, what does that give us?
So alpha 1 has to be h over 2.
Yes.
Beta 1 has to be hf over 2.
Yeah,
Hf ty
hf of ty over 2. So now all the parameters are determined. Just to try to match things up to this point. Okay. So now, so there's no point in going further now that everything's been determined. What we need to look at though is the first terms that don't cancel. Okay, well, in the Taylor expansion of y, so the first expansion I have in the previous board, the first term that did not match up was the, we took care of the first derivative of f, we didn't do the second derivative, but that's y triple prime. So 1/6 y triple prime at an unknown point in the first Taylor expansion, and then this other Taylor expansion, the one of f, the first term we didn't match up is, okay, 1/6 h cubed,
d squared over dt.
yeah, second, oh wait a minute, oh, no, that's the same expansion.
1/6 h squared.
So it's all these terms that involve second partial derivatives of f. So we actually have, for instance, 1/2 second partial of f with respect to t times alpha 1 squared. But all of this in the numerical method is multiplied by h. So I actually have an h here. And what is alpha 1? Alpha 1 is now h over 2. So this is h squared over 4. Plus other terms. But the point is, the leading error terms are order h cubed. So everything up to order h squared matched. So what does that mean? So when the
So the order is, well, the leading term has, error term has order h cubed.
yes,
So which means the thing is second.
it's going to be second order accurate because keep in mind when we define local truncation error, we take the numerical method and we divide by h in the definition I gave last time.
Right.
So what that means is the local truncation error, which I abbreviated last time, tau n of h, is order h squared. Right, so by choosing these parameters right, instead of just the simple choices of alpha 1 and beta 1 equals 0 and alpha 1 equals 1, that's Euler's method, the first order accurate. Now we have our Runge-Kutta or RK method. I can write out in full now. Yn plus 1 is equal to Yn plus hf of Tn plus h over 2, and then Yn plus hf of Tn Yn. So that's the actual method. And this is called the midpoint method. Okay. And the reason for that is we're using the midpoint of our interval in time between Tn and Tn plus 1. We go to a halfway point there. Here, we take a simple approximation to the solution at this same time. Oh, that should be a 2. So, yeah. So this attempts to, this is actually Euler's method right here to approximate the solution at time Tn plus h over 2, and then we use that to plug into f again to try to approximate what's going on at the midpoint, or to try to get the correct slope. So this is just really one of the simplest Runge-Kutta methods you can have, because f is only evaluated once. Well, actually, we only have one evaluation of f here, but to get that, we need to evaluate f a second time. So this is an example of what is called a two-stage method. And by stage, I mean evaluations of f. So I'm going to write this a little differently, because this conforms more to how you would write this if you're implementing this in code. Oh, by the way, Monday, we're in the lab. You can see that on the schedule, but just thought I'd let you know. And we'll be implementing methods like this. And so how you would go about doing this in a way that is conducive to coding is, first, I define a variable, intermediate variable, k1 is hf of tn yn. And then I define another intermediate variable, k2 is hf of, okay, so I do tn plus h over 2, and then I have yn plus 1/2 k1. So this value goes in here. And then finally, yn plus 1 is equal to yn plus, and then all we have there is just k2. So this is the same midpoint method, it's just written differently. But a lot of Runge-Kutta methods are written like this to define, carry out your evaluations of f, however many of them you need, and then incorporate them into getting yn plus 1 from yn. Okay. And these k values tend to build on each other like we have here. Okay, so this is how you design Runge-Kutta methods. You figure out how many evaluations of f you want to have, and then just match up these Taylor expansions. You have a Taylor expansion of the solution y, you have multivariable Taylor expansion of f. You keep matching terms until you can't match anymore, and then whatever doesn't match reveals your order of accuracy. Okay. So any questions about what was done here to figure out this Runge-Kutta method? Okay.
Why are we letting K1 be HF like that?
As opposed to what? Well, because we need it down here for what we're going to plug into the second time.
Right, and for the first time, why do we, like we could have just written down K1 equals that whole thing. HF, Tn, Yn, and then Yn plus K1. Like,
I guess it's from a just maybe from a readability point of view, but so at least each of the expressions here are simple enough. Well, here's one thing. For more complicated Runge-Kutta methods, we evaluate f several times. Anytime you evaluate f, you want to hold on to that because you don't know how many times you're going to need it.
Right. So this is a two-stage. So HF of something, so you need the K1, and K2, you just plug that K1. So if you were to say a three-stage, you'd have three variables.
Yeah, and you'd have three evaluations of f. Yeah, so each stage is an evaluation of f.
So would it be Tn plus h squared over 6?
Wait.
For the three-stage? Not
necessarily. So I'm actually not going to show you a three-stage one here, but we'll see a four-stage one in a bit. Okay. All right. Any other questions about this Runge-Kutta method? Okay. All right. Okay. All right. Now I'm going to show you a couple other run code methods. We won't go through a design and we'll just spit out the final result, but this similar procedure would be used to get them. Okay. So and there are a great many run code methods out there, different orders. Just show you a couple other ones. So one is the modify Euler. Okay. I'm going to write it, it's kind of similar to Euler's method, but then I'll write it in stages. So this one uses f of t and yn, but then we evaluate f of tn plus 1, which is also the same as tn plus h. And then we have yn plus h f of tn yn. So what's happening here is, okay, we evaluate f at tn yn, and then here we evaluate f at tn plus 1, and this, okay, so that equals tn plus 1, that's exact. And this is an approximation of yn plus 1 using plain old Euler's method. But then we plug it into f to try to estimate the slope at that point. So we're taking this slope at time tn, this slope at tn plus 1, and we're averaging them in order to get the right slope to add on to yn to get to yn plus 1. So this is also second order accurate. And it also requires two evaluations of f. So I can write it this way. So k1 is still f of t n yn, and then k2 is hf of tn plus h instead of h over 2 like in a midpoint method, and then yn plus k1, whereas in the midpoint method I had 1/2 k1, but then yn plus 1 is equal to yn plus 1/2 k1 plus k2. So this is different from midpoint method where we have both k1 and k2 involved in the final step to get yn plus 1. All right. Now, let's see how well you remember your stuff from last semester. What integration rule does this method resemble? Because we're evaluating at the endpoints of our interval in time, and then we then average them basically.
What was that quad?
What? No, go ahead.
Oh, I
I thought you said something.
Integration. So Romberg?
One of the simpler rules, like the very basic building block integration rules.
The endpoints, right?
Yeah, yeah, because these are the endpoints of our time interval. So we're evaluating our integrand, which is y prime.
Trapezoidal?
Yes, this is a trapezoidal rule. You wouldn't get that from a name at all. But yeah, what about the previous one? What rule is that?
The other one?
Yeah, that one.
The middle one.
Yeah, yeah. In that case, the name gives it away.
Yes.
It's the midpoint rule. Yeah, because we basically evaluating y prime at the midpoint. Because if you think of it this way, if you have y prime is f of ty, but then you integrate both sides of this from time tn to tn plus 1, that's the same as saying y of tn plus 1 equals y of tn plus the integral from tn to tn plus 1 of f of t, use t, y of t dt. So this is the integral form of the ODE. So you can think of any of these methods as trying to approximate this integral from tn to tn plus 1. How do you approximate an integral? You evaluate f at select points and use the appropriate weights. So Euler's method uses a lousy integration rule. It just uses the left endpoint, like you did in Cal 2, when you're doing all those rectangles and those Riemann sums. It's awful. So that's why it's first order accurate. So we just seen the first Bron-Cohen method that I did. That's the midpoint rule for this, where we pick Tn plus h over 2. And now we see the trapezoidal rule. Okay. All right. So that's one way you can design Bron-Cohen methods. Actually, is you're focusing on how do you approximate that integral. Because the trouble is, you're evaluating f at the solution that you're trying to compute. So that complicates matters. Okay. Now, the best known Bron-Cohen method is fourth order. Now, it's actually more of a 1/4 order, but this is like, I guess, a classic order. When you say fourth order Bron-Cohen, this is one that people generally think of. And that's going to write it in stages, otherwise it'd be way too cumbersome. So K1 is still hf of Tn yn. K2 is hf of Tn. So we go to the midpoint, and then yn plus 1/2 K1. And then K3. So we again go to the midpoint, but now we take yn plus 1/2 K2 to try to get another approximation at the midpoint using a somewhat different slope. And then for K4, we go all the way to the right endpoint, Tn plus h, yn plus K3. Okay. And then finally we combine all of these. So yn plus 1 is yn plus 1/6, and we have K1 plus 2K2 plus 2K3 plus K4. All right. And as the name suggests, this is fourth order accurate. Okay. All right. But of course, it takes more work to get that fourth order accuracy. But because that's how order of accuracy works, your error is so much lower. That extra work is definitely worth it. Okay. So we'll see limitations of this also in the lab. What integration rule does this kind of look like? Yes, it is Simpson's rule because if you lump these two together, all of this is happening at the midpoint. Because remember, Simpson's rule says that the integral of f is approximately b minus a over 6, so that's the 1/6 there. And then you have f of a, which is only weighted once, plus 4 f at the midpoint, plus f of b. So the midpoint gets 4 times the weight as the endpoints. And that happens here if you lump these two together. So it's not exactly Simpson's rule, but it's pretty close. And Simpson's rule, the composite Simpson's rule, is fourth order accurate. Just as a composite trapezoidal rule is a second order accurate. Okay, so take a note here. This is like the course, the midpoint method is like the midpoint rule. Okay. Like I said, there are many more kind of methods that use different numbers of stages to get different order of accuracy. Actually, I think there's a chart in, I think it's in the textbook actually. If you have a certain number of stages, what is the maximum order of accuracy you can hope for? So it's not always as cut and dry as it might seem. But the thing is, unfortunately, as you add more and more stages, you get diminishing returns on what you can expect for order of accuracy. So you might think, if I have 4th order accuracy of 4 stages, if I have 10 stages, I can have 10th order accuracy. But it's not true. You get less and less. So this is a nice compromise between the amount of work you're doing for each time step, because you got to admit, this is a lot more work for a computer to do for one time step as opposed to Euler's method that it'll only evaluate its f once. But the payoff is so great because think this way: if you decrease h by a factor of 10 in Euler's method, your error decreases by a factor of 10. But with this, in 4th order Roncutta, it decreases by a factor of 10,000. So it's definitely worthwhile to put in that extra work. Okay. All right, so questions about these archaic methods? Okay. Oh, so we've been quite a long time. I'm shocked. Okay. And actually, I had come to the end of what well, not quite, but I have extra material on me just in case. But if I don't have time for that, no big deal. Okay. Definitely important, very important concept out of an implicit method. Okay. So all the methods that we've seen, Euler's method is technically a Runge-Kutta method. It's just a lousy one. All the methods that we've seen fall into the category of explicit time-stepping methods. And the simplest way to explain that, admittedly very informal, you can just plug and chug. You just evaluate f at certain points. You have all the information you need. There's no need to solve any equation for them. Okay. So, by contrast, in implicit methods, you have to solve an equation at each time step. Okay. Now, okay. So here are some examples of implicit methods that are actually just slight changes of methods I've already shown you. There's backward Euler. Now, if you recall, Euler's method is yn plus 1 is yn plus hf of tn yn. But backward Euler, we're instead of evaluating f at the left endpoint of the interval in time, we're evaluating at the right endpoint. So tn plus 1, yn plus 1. So what are you trying to compute, though? The output is yn plus 1. So now it appears on both sides of the equation. So you have to solve for this somehow. Now, suppose this is a linear equation. Then that's not such a big deal. You can just take this term involving y n plus 1 and move it to the other side and solve for it. You may have to like solve a system of linear equations, like an inverted matrix. If this is a nonlinear equation, then you have to use the method that we saw last semester for root finding, like Newton's method. Okay. So if nonlinear, use Newton's method or related methods. Okay. Now, that might seem rather crazy, like a whole lot of work, because these are iterative methods. So you're doing a certain amount of work for each iteration to try to get convergence. But let's see how well you remember anything from last semester. Let's suppose we're going to solve this equation using Newton's method. What does Newton's method need? What?
A derivative to exist.
Yes, it does. But in order to work well, that's just to be able to use Newton's method at all, so you'd have to be able to figure out the derivative of f.
It has to be local, like,
Yes, in other words, what you need is
fairly close guess.
a good initial guess. Okay. Let's talk about that, the initial guess. What would be a good choice of an initial guess? Like a natural, logical choice of initial guess that's actually going to be close to yn plus 1. Yn. Yeah, so just go ahead and use that. So now the smaller h is, the better that initial guess will be. But at least you have something to go on. Whereas Newton's method, for the root finding a general function, you might not have any information, you just like cross your fingers. But you don't have to do that here. Another thing you could do is maybe take yn and go ahead and use forward Euler's method. Just to get something that's actually in the neighborhood of time tn plus 1. In fact, in actual applications where you're using an implicit method, a nonlinear system of ODEs, and you need to use Newton's method, it's very common practice to only perform one iteration. Because first of all, Newton's method converges quadratically. Second, you have a good initial guess, so you're already in that neighborhood. And you're just going to reduce that error even more. Also, you might think, well, why not use more iterations? Maybe just a few more to solve this equation of super high accuracy. But let's keep in mind, all of this is an approximation to the original ODE. There's going to be error of order, this is first order accurate, I should mention, just like forward Euler methods. So if you're already committing an error of order h, even if you compute this exactly, why are you going to expend more effort to go ahead and solve this exactly if you're just going, because you're going to have this larger error term no matter what you do. So you might as well save yourself some work. It's okay if you perform only one or two iterations and you have another error of order h or maybe h squared, and then call it good. So that's one thing you have to keep in mind when you're using numerical methods in general. Think about where the problem you're solving is coming from. If there's already uncertainty or error in the problem as it's given to you, then there's no point in expending a lot of effort to solve this given problem with high order accuracy that's going to be where the error is going to be negligible compared to whatever error you already have. You're just wasting effort. So that knowing the context of a problem you have is quite important. Okay. Now, if it's not practical to compute a derivative of f, you could do like some sort of finite difference. And what method is that we saw last semester? That's the secant method. So that's actually more commonly used. Okay, and we'll see more of this later on when we get to solving systems of nonlinear equations and how we can do all that efficiently when because when it's systems of nonlinear equations, you're having to solve systems of linear equations in a process and have to invert matrices. We want to try to do that as quickly as possible.
Then you're going to need 2 guesses for that.
Yes. Well, here could be your 2 guesses.
Right.
Yeah. Okay. In fact, if you're going to use Newton's method in the process of carrying out Newton's step, you got to evaluate this anyway. So. Okay.
And then at least you don't have to care about the derivative existing.
Yeah. Okay. Now, okay, so that's one example of implicit method. Here's another that's quite well known. This is actually called the trapezoidal method, whereas the modified Euler method that looks like a trapezoidal rule is sometimes called the explicit trapezoidal method. And because I was saying trapezoidal, I almost wrote method as methoid. Okay. Okay. So that is, so if you look at this and the modified Euler method from a previous board, you'll see that there's a close resemblance. So h over 2 f of tn yn plus f of tn plus 1 yn plus 1. So what the modified Euler method or explicit trapezoidal does is it can't evaluate this directly, so it tries to fake it using forward Euler. So it replaces this by this. But if you don't care about that, if you don't mind having an implicit method, then you go ahead and use this, and now you solve this for yn plus 1. So this part is treated as a constant in your iterative method. Okay, so and this is second order, just like modified Euler is. Okay. All right, and you'd expect higher accuracy because you're doing a little more work. You're evaluating f twice. Okay. All right. Now, but the thing is, even if you're not doing much work with whatever iterative method you use, you can still see that implicit methods are going to require more work than explicit methods. But here we still have similar order of accuracy. So these are the same order of accuracy as their explicit counterparts, like forward Euler or modified Euler method. So at this point, I could not fault you for thinking, well, maybe implicit methods are not so practical. Why do we have them? So since I still have some time, okay, this should work well. I will focus on forward and backward Euler on a simple equation to give you an idea as to why implicit methods are actually quite nice to have. And this actually gives you a preview of a very important concept I'll cover later, known as stability. Okay. So I'm going to focus on this very simple ODE. Y prime is equal to lambda y, where lambda is just a constant. And we'll assume that lambda is stable initial condition. And we're going to assume that lambda is negative. And we know what the exact solution is. Why not e to the lambda t? Okay. Now, because lambda is negative, the consequence of this is, what happens to the solution?
Zero.
Yes. Because of it, we have a decaying exponential, so the solution converges to 0. So if we're going to use a numerical method for this problem, we would expect the same behavior from our numerical solution. It should be decreasing over time. It definitely should not increase. Okay. So let's look at forward Euler. So yn plus 1 is equal to yn plus h f of t and yn. But now substituting what f is. So that's yn plus h lambda yn. So we're just taking each y value and multiplying it by 1 plus lambda h. All right. Now, what about backward Euler? Okay, so yn plus 1 is equal to yn plus hf of tn plus 1 yn plus 1. So that would be yn plus h lambda yn plus 1. So now we have to solve for yn plus 1. But this is a linear equation, so in this case that's easy to do. We can just take this term and move it to the other side. So yn plus 1 is equal to 1 over 1 minus h lambda times yn. Okay. So in both cases, we're just multiplying yn by something. This is something different for two methods, 1 plus h lambda or 1 over 1 minus h lambda. So no real surprises there. So what that means is we can easily describe what the numerical solution looks like at any step. So in the case of forward Euler, yn is just 1 plus h lambda to the n times y naught. And for backward Euler, we have 1 minus h lambda to the minus n times y naught. Okay. Now, lambda is negative. So we want to make sure that the numerical solution is decaying to 0, just like the exact solution is. So what has to be true of these numbers that I'll highlight here that we're multiplying by in order to make sure we have that correct behavior of the solution?
It has to be less than, it has to be in between 0 and 1.
Yeah, it needs to be between 0 and 1. Okay.
What has to be between 0 and 1?
Whatever we're multiplying by.
Okay.
Yeah, because assuming that whatever sign y naught is, the solution will stay that sign because we multiply by something positive, but also by something less than 1. So, because we're trying to approximate that. So we want to have similar behavior. Okay. So we need. Okay.
In other words, we need lambda to be in between negative 1 over h and 0.
Yeah, so we can take this and solve it for h in terms of lambda. So we have. Okay. Now when I divide by lambda, keep in mind lambda is negative, so that reverses the sign of the inequality. So lambda is greater than h equals to 0. Keep in mind, since lambda is negative, minus 1 over lambda is positive. So this is our condition. for that to work out. Okay, so what that means is we have a restriction on H. So that means that it is conditionally, so forward Euler is conditionally stable. So we only, because we only get a bounded solution if H is sufficiently small. And the larger lambda is in absolute values, so that more rapid that decay, the more severe the restriction. So this is a problem with explicit methods in general. They have this, sometimes, in some cases, severe restriction on your time step. If your system of ODEs comes from a PDE, partial differential equation, where you've done like spatial discretization, the finer your spatial resolution, the larger general lambda turns out to be in your system of ODEs, like the maximum possible lambda, therefore restricting your H even more. So more resolution means smaller time step. So that creates a lot of headaches. So in other words, computing power increases all the time, but the problems get harder to solve numerically. Okay, so that's forward Euler. What about backward Euler? Let's take a look at that. So we need 1 over 1 minus h lambda to be between 0 and 1. Now, first of all, lambda is negative, so we are adding something right here. So this number here is going to be greater than 1. So what does that tell us?
It's already.
What?
It's always between 0 and 1.
Yeah. Yeah, but if there's no getting around it, you can't help but have it between 0 and 1. Because everything's positive in here, and because the denominator is always larger, then yes, this is going to be less than 1. So this is what is called unconditionally stable. Okay. That's what we really like to have, are methods that are unconditionally stable, so you can choose the time step however you like and not have to worry about getting physically incorrect behavior. Now, you still have a good reason to pick h small no matter what, just for sake of accuracy, because your error depends on the power of h. But as long as you know that you're going to get at least qualitatively correct behavior, that's something that really helps. So most methods have conditional stability. There are certain implicit methods, like this one, that are unconditionally stable. You don't generally get unconditionally stable explicit methods. I did come up with one for PDEs, for certain PDEs. It's a pretty narrow category, but at least for those kind of problems, I was able to prove unconditional stability. So this is why implicit methods are useful, because of their favorable stability properties compared to explicit methods. And for PDEs, especially if you have higher order spatial derivatives, people more often use implicit methods. Okay, so that is a justification of why we need it. Even so, what happens is, yes, there is more work per time step for an implicit method, but chances are you're taking fewer time steps. So the amount of work balances out, or maybe puts you ahead using an implicit method. Okay, so any questions about this rudimentary stability analysis? Stability is something we'll revisit after we've seen more methods, but I want to give you a preview based on what little we've seen so far as to why this is an important concept. All right.
Is it stability of the system or stability of the analysis?
Look this way. Suppose you have, like for instance, here we have a single linear equation. So the value of lambda determines your stability condition. If you have a system of linear ODEs, then the eigenvalues of that matrix determine your stability condition.
But if it's unconditional conditionally stable, so that means that it's going to be stable no matter what, as long as you pick like an H wisely.
Well, with unconsciously, what will happen is your solutions will remain bounded as for any H,
For any H.
but they may not be accurate. So you make it something that still decays to 0, but it's still way
It will
off.
take a long time.
And therefore you still want to choose H small for that reason, but for Burton is not great. Whereas for an explicit method, you might not need a particularly small H for accuracy's sake, but you need to pick one much smaller for stability's sake. You have to care about both things. There are a lot of problems where you may not really need all that small an H just to represent the solution, like if it's not changing very rapidly.
Right.
But for stability considerations, you're forced to pick a larger one and a smaller one than you'd want to.
Right.
And therefore do a whole lot more work than you think is necessary. And in that situation in particular is where people resort to implicit methods. Okay. Now, I will finish with a quick word about higher equations and systems. So, okay. So I'm actually jumping a little bit ahead in notes because I didn't have a space for this in the schedule earlier. But I thought, hey, I have a chance to fit it in. Why not? There's not much to say. So any these methods that we see can be applied to a system. There really isn't anything to change even. In fact, what you'll see on Monday is the code that I'll show you, or you might develop during class, works without modification whether you're solving a single ODE or a system of ODEs. So for example, I'll just say modified Euler method, which is also known, so I want you to get this in your notes, the explicit trapezoidal method as opposed to the implicit trapezoidal method that I just showed you. So you're solving the system of ODEs. Y prime is f of ty, where y is now a vector, and f is a vector-valued function. And you have a vector-valued initial condition. So you can say k1, which is now a vector, is hf of tn yn. K2, also a vector, is f of tn plus h yn plus k1. So then yn plus 1 is equal to yn plus 1/2 k1 plus k2. So if you implement f to take in a t value and a y that is a vector, and then returns a vector, you don't have to change your time-stepping method at all. And MATLAB is quite nice in that its functions will take whatever you give it, or you can write it that way, where it accepts a scalar or a vector in certain places, and it just works. So that's what we'll see next on Monday. You just use exactly the same code. And this is very important for instance, higher order ODE. So for instance, y double prime is equal to some function f of t, y, and y prime. So this is a general second order ODE with two initial conditions. So you're posing conditions of y and y prime, and you have two different initial values. Well, how do you deal with a second order ODE? You can always convert it to a system of two first order ODEs. So I'm going to let u equal y and v equal y prime. So now we have this system of two equations. U prime is equal to v. V prime, which is y double prime, is f of t, u, and v. So now I have this first order system, and I have my initial conditions. U of 0 is y naught. U prime of 0, v of 0 equals z naught. So now we're back in first order territory. So now you can use whatever time stepping method like this one for a first order ODE to solve your second order ODE. And then you take the first component of whatever you get out of it, and that's your solution to your original problem. So for instance, if I were to use Euler's method, I'd have un plus 1 is equal to un plus h vn to handle the first equation. And then I'd have vn plus 1 is equal to vn plus h f of tn un vn. So solving these second order ODEs using a method like Euler's method is no problem. But in code, chances are you'd want to vectorize this. You'd have, so this you could think of as h times a vector valued function of t and a vector un vn, where it uses both components here and sends them into f. Okay. So in other words, you have a vector wn plus 1 is equal to wn plus hg of t wn, where wn is a vector consisting of un and vn. So if you look at it from a vector point of view, then everything works out just fine that way. So I know I've just run out of time. What could be changed in this case, this particular case, to make this a little more accurate? Well, how could I change the second line? That might notice here I compute a new value of u up here. And I don't bother using it down here. So, for instance, what I could do is I could make this like maybe an implicit or semi-implicit method, where I use un plus 1, and maybe I plug in tn plus 1, and I could do tn plus 1, un plus 1, and then some approximation of vn. Or maybe I can make this, keep this equation explicit, make this one implicit. So there's some time-stepping methods you can design based on that do different things that might improve your accuracy. Like maybe I could do something like that to make it second order accurate instead of first.
So expressing vn in terms of un plus 1?
Or using approximating vn plus 1 somehow. So there's different things you can do. And I think actually one of the exercises that I haven't assigned yet does something like this to improve accuracy. So when you have systems, you can take advantage of more up-to-date information. Okay, I know I'm way over time.